All right, what we're going to do in section 3.4 is we're going to use some of the stuff that we've learned about derivatives now to start looking at some real problems, okay, and what kind of things that we can do by finding derivatives. And we're going to start out with one. This is actually in your binder. Remember the AP problems that I gave you? This is on the back page of the first sheet, and it gives us the volume of a tank of water at t minutes. It's given by this cubic function q of t. And the question is, it says determine the average rate of change in gallons per minute of the volume during the time interval 0 to 3 minutes. Okay, so with that said, the key word here is finding the average rate of change. Okay, if we wanted to find the instantaneous rate of change, remember that would be a different question. Okay, we'll get to that question in a minute. But if we want to find the average rate of change, okay, just like we did with our other rate of change problems, okay, we're just essentially calculating the slope between the endpoints. Okay, the change in y over the change in x. Okay, that's what a slope is. It's an average rate of change. So knowing that, if we take a look at our q of t function, okay, and we find the 2 points they gave us, they asked us to do time 0 and time 3. Okay, and if we put in 0, we're going to get 1. So the one endpoint is 0, which means that at time 0, there's 1 gallon of water in the tank. At time 3, if we plug a 3 into it, we're going to get 70, which means that at time 3, after 3 minutes, there's 70 gallons in the tank. Okay, and then after that, again, recognizing that when we subtract the y's and subtract the x's, it's kind of a giveaway as to what we're finding, because we're just dividing gallons by minute, which means that our unit here would be gallons per minute. Okay, we're finding the average rate of change, which of course is 69 on top, 3 on the bottom, and we get 23 gallons per minute. So that would be the average rate of change, okay, for the time frame 0 to 3. Now, knowing that this is a cubic function, if we picked a different time, let's say we did 0 to 10, okay, are we going to get 23 gallons per minute necessarily? No. Okay, the average rate of change is essentially, in this case, and like every case, the change in the y-coordinates over the change in the x-coordinates. It's just a slope. Okay. All right. Now, if we wanted to find the instantaneous rate of change, which we weren't asked that in this particular question, but I'm going to ask it now. Okay, if we wanted to know the instantaneous rate of change, now we're talking about the derivative. Okay, because if we could find the derivative, then we could find the rate of change at a particular time. Okay, how is the rate changing at a given time? So if we find the derivative, of course it's just a power function, so we can use the power rule, 3t squared plus 8t plus 2. Okay, and so say for instance we wanted to find the rate of change at time 2. Okay, I want to know what's going on at time 2 with this function. How is it changing? Okay, if we plug a 2 into our function, it turns out to be 30. Okay, again, it's still a gallons per minute because the derivative is a slope, okay, at a particular point. Okay, no different than a slope from 2 points. Still a slope for this function. Okay, and again, looking at a picture, if I had this q of t function, whatever it may look like, okay, if I find the slope at 1 point, okay, again, key issue is it's still a slope, okay, which means that if this is measured in gallons and this is measured in minutes, then any slope I calculate is going to be gallons on top, minutes on the bottom. So whether I use 2 points or 1 point, okay, we'd still get the same units here, and that's an important fact. Okay, so even though it's an average rate of change here, an instantaneous rate of change here at time 2, okay, we still have the same units. Okay, it's still something gallons per minute. Okay, all right, questions so far? Okay. All right, so in this particular case, again, you know, nothing we haven't already done, calculus and algebra-wise. Okay, we just want to make sure that we're recognizing here that what we're getting when we actually find the derivative. Okay, what does it tell us? And in this particular situation, it's telling us the rate of change, okay, for the water flow here. How much water is going into the tank at a rate of 30 gallons per minute at that particular time. Okay, and we can figure that out at any particular time because we have the derivative now. Okay. All right. I want to look at the next problem I want to look at. It's another application problem. Is number 3 from your book, page 129. they, in number 3, have a projectile problem. Okay, and we have seen some projectile problems so far. Okay, we're going to spend some time on this because you'll notice that the title of this section is Velocity and Other Rates of Change. Okay, so we're going to revisit this idea of position, velocity, and acceleration we've discussed a few times already. Okay, we're going to look at some more problems. Our homework problems are going to be dealing with some more problems that are like this and like other rates of change problems. So what it boils down to is they've given us a position function here. This S function tells us our height of the rock at any time. Okay, and the 24t minus 0.8t squared. Remember the variables here are height, okay, which is S, okay, measured in meters. Our t represents the time, okay, measured in seconds. Okay. And in our question that we're asked in number 3, it says find the rock's velocity and acceleration as functions of time. Okay. So if we want to find the velocity, okay, we know that the velocity here is going to be the change, okay, in position over change in time. If we want to find an average velocity, if we want to find the instantaneous velocity, we're going to find the derivative. Okay, the derivative of the position function is a velocity function. So knowing that, if we go ahead and find the derivative, so S prime is equal to V, and the derivative of the position is always equal to the velocity, okay, which in our case is just a power function, so we can go 24 minus 1.6t, okay, and that gives us the velocity function. Okay. And as we discussed the last time, if we want the acceleration equation, okay, the acceleration is the derivative of the velocity. So if we find the second derivative of the position, which is the derivative of the velocity, okay, that gives us the acceleration. And the acceleration in this particular case is a constant this time because we have 0 here for this one. This is linear, so it's just negative 1.6, and that's the acceleration. Okay. And you notice that the acceleration is constant, okay, because just like on Earth, if we're on the moon, okay, there's gravity. Okay? And as soon as the rock leaves our hand, the only force that's acting on the rock is gravity. You notice that it's quite a bit less than what it is on the Earth because we know from videos and whatnot and people telling us that if we're on the moon, if we throw something, it doesn't come down to the ground near as fast as it does on the Earth. True? Okay. So we should expect that the number be smaller because our gravity constant on Earth, we have a bigger pull on Earth than we do on the moon. Okay, so this is our acceleration equation. All right, now we're going to answer a few questions then with these two equations that we've just written. And the first one is how long did it take the rock to reach its highest point? Okay, so if we're talking about highest point, okay, let's think about what that would look like. Okay, if we have a position equation, if we were to graph the position equation, we know that it's a parabola, okay, because we can see the position equation, it's quadratic. Okay, and again, the question is how long did it take the rock to reach the highest point? Well, the highest point would be here. Okay, what do we know about what's going on at the highest point? Okay, yeah, at the highest point, the derivative would be 0. True? Okay, because it's a maximum point, and at this maximum point, the derivative is going to be equal to 0. So if we want to answer the question in part A, we need to take the derivative and set it equal to 0. Okay, so similar to finding horizontal tangents, okay, it's exactly the same. We want to find where the tangent is horizontal. It's going to be where the derivative equals 0. So if we set the derivative equal to 0 and we solve that sentence, we end up with 15 seconds, 1.6 into 24. Okay, so at time 15 is when the rock is going to reach the maximum height. Okay. Part C says, how high did the rock go? Well, I want to know how high the rock went. Ultimately, if this is, again, this is my S function here that I've drawn a picture of. Okay, if I want to know the y coordinate at that point, I already know the x coordinate, I figured that out. If I want to know the y coordinate, I'm going to put that into S. Okay, because S gives me the height at any time. So if I put 15 seconds into my equation, okay, I can go ahead and get the answer of 180 in this particular case. Okay. So if I plug 15 into my position equation, I'm going to get 180. And that's, again, the y coordinate of the maximum height point, which is how high the rock went. We'd say it goes 180 meters in the air. Okay. Questions so far? All right. The Part D question says, when did the rock reach half of its maximum height? Okay, when did the rock reach half of its maximum height? Well, we know the maximum height is going to be 180, so half of the maximum height would be when the rock is at what? At 90. Okay. So, with that said, wouldn't that right there give me the answer? Okay. This is my height at any time. We want to know when that's equal to 90. So if we solve that quadratic equation, okay, we should be able to figure out when that occurred. True? Okay. So with that said, if we find the answer to this, we can remember it's a quadratic equation, so we could solve it in several different ways. We could factor if possible. With that 0.8 in there, we might want to multiply everything by 10 so that we can get the point out of there, so it's easier to factor. Okay. We could use the quadratic formula. Okay. We don't have to use factoring. We can just go ahead and use the quadratic formula and find the answer. Okay. If an estimate is okay, then we could use the graphing calculator and find the intersection points between the quadratic and the constant. Okay, so there's lots of different ways we can find the answers to that. Okay, but bottom line is for us, we just need to make sure we recognize that to set the equation up, we want to know when, okay, is the position equal to 90. So set the position equation equal to 90, and we're good to go. Jake?
Would that have two different answers then because it's a parabola?
Yeah, knowing what we know about it going up to 90 or 180 is that we should, when we get done, there should be two different answers then, shouldn't there? Absolutely. Okay. So one of them is going to be before 15 and one of them is going to be after. Okay. If you don't get that, then knowing the physics of the problem, you'd know something was wrong, right? Okay. All right. And then how about part E? How long was the rock aloft? In other words, when did it hit the ground? Okay. Well, if it hits the ground, okay, what would be the case of the position? The position would have to equal what? Okay. So wouldn't that right there give us the answer? Okay, setting the position equation equal to 0. Okay, if we set the position equation equal to 0, in this particular case it's got a t, so we could do that without the quadratic formula. We could factor out the t. Notice that one of the answers we get is 0, okay, which makes sense because we threw the ground, we're assuming that throwing it started on the ground, it's going to end on the ground. Okay, one of the answers is 0. Okay. The initial height in the problem was 0, so we should expect that one of the answers here is 0. The other one's going to be 24 divided by 0.8. Okay. And if you divide 24 by 0.8, the answer is 30. Okay. And again, looking at our picture, if it's at the maximum height at 15, is it surprising that it's back to the ground at 30? Okay. Knowing what we know about parabolas and their symmetries, okay. If this is defined by a parabola, shouldn't it be 0, 15 at the max, and then 30 when we're back on the ground at the same spot? Okay. If it wasn't 30, we'd have a problem, wouldn't we? Okay. Because it's a, like I said, it's a parabola, and we know parabolas have symmetry. Okay. One other question that I might ask you that's not asked in this problem, though, is when it hits the ground here, if I go back to my picture, when it hits the ground at time 30, 30, 0, and 0, 0, okay, we know it's going to hit the ground at time 30. Okay, how fast is it going when it hits the ground? What do you think about that? Yeah, ultimately, if I want to know how fast it's going, what gives me the velocity at any given time? Okay, doesn't the velocity equation give that to me? So couldn't I just put time 30 into the velocity equation and get the velocity at that particular point? So if we do that, let's see what it is. Our velocity equation is 24 minus 1.6 times, in this case, 30. Gives us an answer of negative 24. Keeping in mind that the velocity is going to be measured in meters per second. True. So it's going negative 24 meters per second. Now, one thing that we're also going to look at in this section is the official definition of velocity and the definition of speed. Okay. The velocity is what we call a vector quantity. Okay. And to make it simple, we're just going to write this. The velocity has a sign. Okay. And when I say sign, I mean plus or minus. Okay. So when we calculate a velocity here, it really shouldn't be surprising that it's a negative 24 that we get, because the direction that we're going is a negative direction. Okay. The rock is going what? It's going down. Okay. So the fact that the velocity here is negative 24 meters per second. Okay, not only indicates the magnitude part, okay, how fast it's going to us, but it also indicates the direction. Okay, so the velocity is always going to have a magnitude part and a direction part. The direction part is the plus minus. If we're talking about vertical motion, of course, negative means down. If we're talking about horizontal motion, okay, then that means we're moving to the left. Okay, if we're moving right, the velocity should be positive. Moving left, the velocity is negative. Okay. Now, speed is defined as follows. Speed is equal to the absolute value of the velocity. Okay. So, in terms of speed here, we would say that, again, in this case, that the velocity is negative 24 meters per second. Okay, but we would say that the speed is 24 meters per second. Okay, so speed, if we ever gave a negative answer for speed, would that ever be right? No, speed is always positive. Questions so far? All right, one more final question on this one is, at time 30, just before it hits the ground, okay, what would be the acceleration of this rock? It would be negative 1.6, wouldn't it? Okay. In fact, if I had said that for any time, your answer would have been what? Negative 1.6, because the acceleration, okay, the only thing that's making the rock accelerate is gravity, and no matter where the rock is in the air, okay, the acceleration on it is negative 1.6. Okay, it's bringing it back down to the earth at that rate of negative 1.6. And one other thing I didn't address yet is how about the units on this? Okay. If you told me the answer was negative 1.6 for that question, it would be negative 1.6 what? Meters per second, or meters per second squared. So if we had to answer that question, we'd write negative 1.6 meters per second squared. So that would be the acceleration at time 30. And it would also be the acceleration at time 5, at time 10, at time 15 when it's at the top. Okay, and so on. Questions so far? Anybody else have a question?